Valve announced the Steam Frame, Steam Machine, and Steam Controller yesterday. We covered all that in detail, but we have more. This video goes deeper on the engineering of the Steam Frame VR headset specifically. Normally, we don't record every minute of our time with the company, but Valve was cool with it, and we had 2 separate deep dive discussions with Valve's engineers about the Frame VR headset. We didn't want to just let that great, highly technical content go unseen. For example.
Yeah, so lasers are great because they're non-contact, and so you can capture the motion without interfering.
All of those vias are actually working as a thermal transfer through the PCB itself.
Best way we're able to get those fast transition times at the higher frame rates is through the warmth of the device.
So in this video, we'll talk with Valve's engineers about some of the acoustic considerations.
It has some amplification from its location, so and then you take all that back into the software layer, and you see the sampling rate of the IME. It was a little complicated.
Some of the thermal solution design.
So when we told Michael that we wanted to flip the SoC to the opposite side, he immediately started thinking about those power management ICs and was like, oh man, you're killing me. This is the worst thing ever.
And some of the PCB design and layout challenges.
There's a lot of impedance requirements. So everything wants to be really close to where it has to go. But you can't really concentrate all of that heat. So it was definitely a packaging exercise.
We're not going to heavily edit and produce this, so you're going to get basically the raw conversations that were just us talking, not intended for camera, but we captured it anyway just in case it was useful, and it was. Valve made sure to have engineers from basically every aspect of the hardware available, which is awesome, and so we were able to get pretty much all of our questions answered. These are fairly casual conversations with a lot of detail to learn about the relevant sciences and Valve's hardware engineering process, so let's get into it. Before that, this video is brought to you by Haven and their new BF360 Flow case. The Haven BF360 Flow is a high airflow case with a focus on performance, with the model that includes fans using 2 180mm front intake fans at 40mm thick, in combination with a 120mm rear exhaust fan. In our previous testing of the case, we found its thermal performance to be among the best performers on our charts. The BF360 uses a scooped shroud near the GPU that our smoke testing found deflects the air into the leftmost GPU fan for more targeted GPU intake. It also has marked cable management channels, rubber grommets on most metal contact points, and what we think is overall good build quality. Learn more about the Haven BF360 Flow at the link in the description below.
Maybe a year ago now, basically, we sat down and we said, okay, how can we really, really squeeze the maximum thermal output from this guy? And so we literally took the board, mounted it up to a water cooler, and then looked at actually the thermal performance of the heat going out of the backside of the board, as well as actually directly off the top of the SoC. So it's pop memory. So you essentially have the main SoC plus the memory stacked on top of it. That's actually going to impede the heat. Right?
Is it vertically stacked?
Yep.
On the silicon?
Exactly.
Okay.
Yep.
Yeah,
so
it's just package on package. So the memory chip solders on top of the SoC.
Cool.
Exactly.
Cool.
Yeah, so essentially you can think of it as, 2 direct paths where heat could go, either through the pop memory up into a heatsink, or you could actually go straight through the board. Yeah, and if you think about it, like in the case of an SoC with a ton of vias, right, all of those vias are actually working as a thermal transfer through the PCB itself. So essentially what we did is we said, okay, let's just throw out this idea here. Maybe we can actually pull more heat out of the backside of the board. So we moved a number of components around so that instead of there being a number of capacitors, inductors, all of those components, let's kind of shove them all to the side and then create these big pads that we could actually clamp an additional piece of metal to. And then that would be where we'd actually connect a second heat pipe to.
On the back side of the PCB, is it relatively bare there?
Well,
on the back,
so this is actually the back side of the PCB, effectively, that you're looking at right there. So we moved the SoC actually from this side here originally to the back side. And so that area normally is where you would have a bunch of components that are just, bypass capacitors, a bunch of components that would be critical to driving the SoC. But normally they're just kind of placed there. That like, oh, here's a good location. And we said, we worked closely with Qualcomm and saying, hey, can we figure out how to kind of move things around a little bit, because we're really trying to push this thing super hard. So we created these keep out areas that allows us to have additional elements that clamp down, that actually couple super well to that heat pipe.
Is this a thermal putty under the the cold plate? Okay. And then I guess 8mm flat heat pipe? 6 or 8?
I don't know the exact
That sounds
dimensions.
like a roughly correct number. I can check on that. For you.
Anything? Is it just a fin stack up here, or is there any
That is-
components?
No components up
Okay.
there. Just a fin bank that's been welded essentially to that to the heat pipe. there.
Okay, are you soldering to the heat pipe
Yep.
or welding to
Yep.
it?
Yep.
Okay.
It's directly connected
Cool.
there. Yeah.
Okay.
For the most part, on the aluminum side, the other heat pipe, there's a cutout that goes down and touches the SoC
Oh,
top.
okay.
And then that heat pipe is bonded to the
Got it.
To the mid wall.
mid-wall.
Yeah.
Yeah.
Cool. Very cool.
Yep.
Um,
Yeah, so basically, you can imagine a scenario of different kind of ways that people would connect the thermal solution
Right.
on these types of SoCs. One would be no thermal solution at all. Then maybe they would have a heat spreader, and then maybe they would have maybe a heat pipe that would actually go to some other place, whether it's a phone or
Right.
something like that. In this case, we're basically saying dual heat pipes. We're saying, a big fan that's going to be moving a ton of air. That fan can run. I could get you some more precise numbers or whatever, but it gets loud, right?
Right.
Like if you're running it at the
you're really
maximum,
running,
yeah. We're going to have a sweet spot that's going to be you're going to be happy to be, running it as is, but. If for power users that are like, I want to just max this thing out and see what it can do, that'll be an option.
the question I'm going to have at the end of this is how much of the air flowing through other locations on the device is to cool sort of periphery components on the PCB. But the two considerations would be you're obviously limited on sort of total porous area you can even pull air through to begin with.
That's true. Yeah.
And so puncturing everywhere lets you pull more in just in total. But then, secondarily with the deck OLED in particular, I remember talking about how the OLED had moved some components around to better guide air as it comes through the inlet across those components.
That's definitely a consideration.
Yes. Yeah. So is there anything heat sensitive, particularly beyond the SoC?
Yeah, definitely. So there's a Wi-Fi chip that's depending upon what kind of mode you're operating in, it's going to put off some power. There's also when you're looking at the power delivery network that actually goes, from the battery ultimately through the various regulators that are taking that battery voltage and dropping it down and delivering the power into the SoC. Those are not 100% efficient. So some of the components that we're touching off right there are also the power management ICs that are. This is stuff that Michael spent inordinate amount of time
So is there anything
trying to pull heat out of those as well.
I'm glad you mentioned because I wasn't sure if I should even bother asking or not. But VRM is often like, it's in a lot of devices it's almost a commodity where the VRM is the voltage regulator is just kind of like a given and it's not super interesting. But is there anything particularly special or that required more creative engineering, I guess, on the VRM side?
It was definitely a packaging challenge, I would say. It's a lot of power that we're able to generate, so trying to get everything tight. There's a lot of impedance requirements. So everything wants to be really close to where it has to go, but you can't really concentrate all of that heat. So it was definitely a packaging exercise. For sure.
So when we told Michael that we wanted to flip the SoC to the opposite side, he immediately started thinking about those power management ICs and was like, oh man, you're killing me. This is the worst thing ever.
All the rails that have to move. And
you killed my dog.
Exactly.
So what is that? How does that, what does your job look like, I guess, when you are trying to figure out how to meet the packaging or the density considerations? Are you in software just moving things to see what fits, or are you running calculations?
There's definitely a little bit of that. There's a lot of simulation for sure, especially for impedance requirements. The temperature pieces are a little bit more challenging to simulate for some of that. Because it's only as good from a sim as the whole system, which is relatively difficult to simulate. But yeah, kind of all of the above.
Got it.
Yeah, so along the way, what we did, because we're just like, hey, we're an engineering company, right? We're just like, this is the kind of stuff we really want to like nerd out on. Is like, we're like, how many temperature sensors can we add in there? You know, can we ship with those? You know, how many power measurements can we get in line? And the answer is we put a whole bunch of them in there. Michael could probably give you exact details, but the general idea is, you know, we're able to measure the power on these Qualcomm SoCs. You typically have, there's a series of temperature measurements that are in the SoC itself, a ton, and those are really accurate, and you basically need those for everything. And then there's also the ability to breakout power rails that are dedicated to different CPU clusters as well as the GPU. So you can imagine you've got, you know, one CPU cluster that would be the cores 0 and 1, and then there's a different CPU cluster for cores 2, 3, and 4, and then a different one for 5, 6, and 7. And those 3 different cores have dedicated power rails. So we actually put inline power meters directly for each of those for the CPU, and then also the same thing for the GPU. And then I kept telling Michael, like, hey, how many more can we get in there? So we have a number of other ones as well that we've broken out. So we really have a pretty good map of the power flow in the device as far as like efficiency, you know, how much power is actually making it into each of the different CPU clusters. And so when we're playing a game or testing things out, we can say, okay, this game is CPU you know, intensive, this game is GPU intensive. Here's what the curve looks like when we're tweaking the GPU or CPU frequencies. Here's what it looks like from device to device. You know, so we're just getting tons and tons of data, and then we're also getting all the temperature data.
On top of that.
How many sensors would you say we have for the thermistors that we've placed externally? Not directly on the SoC itself.
I don't remember the exact number.
But like, I don't know.
Ballpark, it's like 10 thermistors and probably like 30 die temperatures, scattered throughout, and a lot. So we can draw a pretty good map.
Is the fan basically
able to use all of that data?
Is it responding to those thermistors?
Yeah, so we have a totally custom fan curve. You know, one of the great things with the open source model, you know, this is running Linux, it's SteamOS, you know, we write all of the kernel drivers, you know, we're interacting with the folks upstream. We're benefiting from what we've learned on the Steam Deck as well as Steam Machine. So so we have algorithms that are running that are essentially reading all of those data points and saying, okay, which one is going to actually give us the best data for this type of a load? In other cases, we might say, you know, we could have different profiles. We could have a variety of different things. So that's stuff we're actually working on right now. We've even been doing some airflow studies, you know, flowing through the device. I'm not sure we want to show on camera exactly yet, but we do have some stuff that we could just show you to kind of give you an idea of the types of stuff that we've been doing. We have a video we could show you.
Smoke testing was mentioned earlier. Yeah, that's cool. Any other special challenges, things that you want to draw attention to? You know, things that you overcame that you want to point out?
I mean, that one's probably like the most complicated. I think in any device that you know, has this many things coming together, we've really had to optimize the data flow essentially from the cameras, from the displays, or going obviously to the displays, the wireless link, and really all of this is, there's a lot of demands on the memory, right? So you have, it's, like I said, it's LPDDR5X, it's the, you know, 4266 as we were discussing. And, you know, so you really have to optimize all of that. So you know, if we're going to be running the cameras at the same time we're running the GPU and also running the CPU as well as the displays, all of that puts a demand on the memory. So that's been a big thing where we've had to really do an awesome job there.
I guess you've kind of got almost two thresholds thermally. You have the threshold where the SoC and the other components cannot operate above a certain temperature.
Definitely.
Right, and then you have whatever the human, like the user's sensitivity is to the device on their face. So do you trip the SoC sensitivity threshold before the user threshold is a problem? Meaning,
that's an interesting question.
You get where I'm going with that?
Yeah. I would say that, I mean, we're using these devices every day. We all are pushing the limits of these all the time. So it's hard to say where a particular user would be saying, okay, this is uncomfortable to wear. You know, if we were running it at the absolute max level. But we're doing a really good job of decoupling that thermal interface that's up here from the user.
Right.
So, and that's the type of stuff that, if we were putting it on our head and saying, hey, this is uncomfortable, then that would definitely be totally unacceptable.
Right.
So, that's the type of thing where, we don't believe that that's going to be a common complaint from users because of the way that we're designing it.
Yeah.
But if you weren't controlling for that, for sure, that could be problematic.
Right.
So yeah, so we're definitely.
I mean, it's going to get warm just from putting your face in goggles,
Totally.
And
exactly.
so that's kind of what I was curious about is
Right, yeah.
does the rest of the device contribute meaningfully?
Yeah, I mean, there definitely is a contribution. I think that's a little bit TBD as we're sort of locking things down. But definitely, that's a huge consideration to us is comfort, right? So we're definitely going to be saying, this is going to be something you're going to be happy to have on your face for a long time.
Right.
So
Cool.
yeah. But I would say that one thing that we worked on pretty extensively together is if you think about all the power that we're trying to put into this for the SoC, that power delivery network from the battery all the way through to driving the displays and driving the SoC. As you can imagine, with anything where you're trying to get a lot of performance out of it, you look at a motherboard and it has all of these crazy capacitors and all of the stuff that's really closely located. Putting it into a head-mounted form factor and having it be a battery powered device, a lot of challenges there. So this is the kind of stuff that Michael here definitely
I would guess
had to look at transients and all of that kind of stuff.
On some of the denser boards we've looked at, like the RTX Pro 6000 Blackwell board is a really good example of density of power components. And I know for them, unfortunately, I guess, in one way, the solution to solving the we don't have enough space problem was, unfortunately, spend more money on better parts. Because that was the way to get the density they needed, Smaller inductors that do the same work, things like that. So.
Yeah, and we definitely have been. This is on the premium side of those types of components, especially. It's like this is the type of thing where we're saying, hey, we want to be able to run this thing flat out, and we don't want any limitations in there. And ultimately, with it being a head-mounted device, there are going to be some thermal challenges, of course, but that's been top of mind from the beginning, right? So,
how long have each of you been working on this?
So I worked on Index. One of the reasons I work a lot more now on SteamOS type stuff, but I worked on the main board a lot on Index, and then immediately started working on this. So I've been working on this for 6 years, basically.
Wow. Okay.
Yeah.
And I'm just over 2 years.
Okay. Cool.
Working on it. So.
Very cool. Yeah.
Yeah, but kind of typical thing at Valve. We're working on things for a long time, and when it's ready, then
it's ready when it's ready.
It's ready when it's ready.
Yeah. Yeah. Cool. Well, that'll be a good one for. We'll close that out here, I guess. So, I appreciate it. Thanks for.
All right. Thanks a lot. Yeah. Appreciate it.
Thank you. What's going on internally on this piece? Is it cable routing or?
So we call this the head strap, and so if you look at the center here, there's a connector. And so you can get power, and there's also a USB-C on the back, so you can get power and data into the core module, which you're holding. On the side here, we have integrated audio, and so if you see this bump out right here, this is where the audio is located. Okay. There are actually 2 drivers per side, and so the thing that's really interesting is when you integrate audio into a sensitive piece of equipment like the core module, where there's all sorts of tracking that's happening. The vibrations can be a limiting factor in terms of how loud the system can get. And so we've designed it with 2 speakers per side. They're actually oriented in different locations, in different orientations, so that they can cancel the vibrations at the IMU and the core, while actually still doubling the amount of sound that the user is getting. Okay. And so there's also the battery in the back, which is sort of a head-shaped conforming multi-cell battery.
And then I guess an external cable going to the battery, is that right?
That's correct.
Yep.
Okay.
And then with the Type-C port on back, if you want to extend it on your with a hip pack or even play indefinitely plugged into the wall, users are free to do so.
Right, okay.
And this battery pack is 21.6 watt hours.
There are inlets on the bottom. Those pull the air in. There's a centrally located fan on top, and then the warmer air comes out at the top.
Got it.
That's designed to keep your face cool so you're not exposed to that thermal
Right.
energy. I know, Joy, you actually did some visualization. on
Yeah,
this
actually,
recently.
there's a clear version in the other room. And so that model we actually use to blow smoke into the system.
Cool.
Because there's many different inlets. There's a front side to the thermal cooling and also a back side as well. In the clear unit, you'll see a heat pipe that carries the heat from the SOC to the heat fin bank at the top. But actually, internally, there's a secondary heat pipe,
Okay.
and it's cooling from the back side of the PCB. So making sure that we can drive this to the absolute limit of how much power that you can pull from this chip.
So is the heat pipe, I guess, routed? Is it just directly over the SOC?
Yeah.
Okay.
Yeah.
On
So
both
there's
sides.
on the top side, there's a direct connection, but we actually pull heat from the back side as well through the PCB.
Right. I don't know a ton about, like I said, the sort of lower power parts, like ARM parts, but at least in a desktop, VRM also contributes a decent amount of heat, depending on what it is. So are the FETs any consideration in terms of cooling for this, or can you just push air across the MOSFETs?
There is an amazing number of thermistors in this.
Okay.
I think you can get the exact number from the hardware system engineer who's in the other room. It might be something like in the 40s. And so there's a number of things that we're interested in cooling in terms of also the cameras, but also the displays themselves get quite hot.
Okay.
So when you look on the clear unit, you're going to be able to see inside, but there's a front chamber and a back chamber, and we specifically have the air drawn in through the back across the displays to cool them down.
Okay.
And so there's a lot of analysis and a lot of ongoing processing, dynamic processing that's happening.
How sensitive is the display to thermal, or is it more of like getting heat off of the user?
No, the display behaves really well when it gets warm. It's actually a benefit.
Okay.
One of the things you want in VR is fast transition times because we run at such high frame rates. I haven't explicitly said it, but we work on the low end from 72 all the way up to 144 hertz.
Okay.
And the best way we're able to get those fast transition times at the higher frame rates is through the warmth of the device.
Okay.
So you can go too far, of course, right? Like a lot of heat. This is an LCD system. A lot of heat in an LCD isn't good, but there's this happy medium in between where the device is warmer than ambient and can therefore achieve really fast times.
What should I know on the acoustic side?
So for the audio side, we mentioned the built-in speakers, which are in the modules over here. There's also 2 microphones on the bottom.
Okay.
That's a broadside array to pick up a really high-quality voice. And then, of course, we designed the audio to be anti-vibration so that you can have a fully integrated system. The overall system is extremely light, so we also designed the audio system to be extremely light as well. And that is primarily...
Anything... So I only know a few audio buzzwords. I'll do my best to use all of them.
Sure.
Is there anything special about like the drivers or the diaphragm or anything like that?
Sure. So there's 2 16-millimeter miniature drivers in each side. You can see here that they are pointed toward your ear. We have this metal grill with a secondary fabric mesh underneath that provides some dampening. And so we have these 2 drivers. They're located in an orientation about 150 degrees relative to each other, and they move in opposition. The sound travels here towards your ear. We've integrated the Steam Audio SDK. So for games that are non-VR, that you might normally experience on a speaker system or on a headphone system, we can apply our spatial processing for those games.
You had mentioned trying to account for vibration, I guess, generated elsewhere in the unit.
Sure.
So I guess are there any, I guess this is for the other guys too, but any challenges you ran into during engineering on the acoustic side or anything you were working on where was something that was actually kind of a monumental thing to clear?
Yeah, absolutely. So for this system, when you want to make sound, you want to have the largest speaker diaphragm possible, so you can move as much air as you possibly can. We call that volumetric displacement. So when you're trying to integrate into the system, this is challenging because you have a very curved surface. And so if you're trying to put a large singular diaphragm, it just doesn't fit.
Right.
It's the square peg in the round hole, if you will. And so what we had done is we had separated that into 2 separate drivers. And then what that also allows us to do is make a lighter weight system, because the larger a system becomes, the more of a secondary suspension you need to have so it can support its own weight. And so by having two smaller drivers, we're able to have a much lighter system. And then in early prototypes, when we had these two drivers located on the side here, they were actually oriented in the same location. And so people wanted to turn the volume up, and they kept turning the volume up, and I kept adding more bass. And next thing you know, the entire screen was jumping and jittering in time, in time to the music. And so we did a lot of measurements. So we have a lab here with a lot of accelerometers, a lot of lasers. There's an IMU on board, so we're able to pull all the information off of there and to really hone in on the types of frequencies and sort of dive into the tracking system to figure out what the issues were.
Right.
And then it ended up being relatively simple because we'd already designed the system to be form factor friendly and already have these two drivers. We're able to swap one. It is a packaging challenge. It was very difficult to get it into the system, but it works extremely well. And we were measuring 18 times less vibration into the IMU, and so we don't have any of that visual jitter.
What's the metric for vibration? How is that actually quantified? Like, what's the actual unit of measurement?
It's interesting because there's a displacement, but then there's also velocity and there's also acceleration. And so if you remember from Physics 101, it's just derivatives of each other. So you can use any one of those metrics. But usually you would use acceleration is pretty easy to measure.
You mentioned lasers for measurement. My memory of that was the laser is basically used to detect these like micro movements in the inductors.
Yeah, so lasers are great because they're non-contact. And so you can capture the motion without interfering. And so sometimes when you have a microphone, you can pick up sound, and you pick up absolutely every single sound. And so your ear is really great because it's paired with a brain that just naturally goes through and say, that's this sound, that's this. But a microphone's pretty dumb. And so if you can shine a laser on something that's moving, and then you have an audio signal as well, you can do some coherence measurements between the two, and you can just say, hey, this part of the sound is actually due to that particular pinpoint location on that device.
So are you kind of mapping like the spectrum, the frequency spectrum, to figure out which part of the spectrum is causing the vibration? Is that
absolutely
okay?
Yeah, it's interesting. When you have a speaker system, there's certain frequencies that move more than other frequencies. And in this particular device, it wasn't actually the frequencies that moved the most that were causing the most issues in the tracker. We had to really figure out how the energy was going from the location that the speakers are. You notice there's a separation between this gasket and the frontal core. So it's not necessarily like a direct path.
Right.
And then the IMU, where it's mounted in the system, has some amplification from its location. And then you take all that back into the software layer, and you see the sampling rate of the IMU. It was a little complicated.
Cool. It sounds like it blends the mechanical side too, right?
Oh, absolutely.
If you're trying to isolate, I guess, or because it seems to me like you would be through the whole process, you're trying to preserve the drivers you want to use and the actual like acoustic hardware you want to use, and so I guess you probably try to deploy whatever mechanical solutions you can to isolate first, and then I guess you eventually run out of space to do things like that. So
yeah, and in this case, there's a lot of signal processing, like high-pass filters, low-pass filters, and there's the mechanical analogs of that in terms of what a high-pass and low-pass were. And we absolutely looked at that, and we're like, well, we need to get rid of these particular frequencies, so we're going to try to add something that's softer. But then that introduces issues because now your tracking system isn't rigidly mounted, and so you really need to, you need to consider the acoustic portion and the sound quality and what you need to accomplish there. There's the mechanical mounting requirements for IMUs, and then there's a lot of software and a data analysis in terms of what's actually happening under the hood, because the frequencies that are causing issues from the audio are actually aliased in the system. So it gets really multi-domain, and we had a task force of people across the different parts of the system. We got together and said, this is how we would solve it if we did it purely mechanically, if we did it purely in software, if we did it purely acoustically. And I think we ended up just solving it purely acoustically. It actually ended up being the most simple.
Does this sort of thing end up getting tested through like a HATS system or anything like that, where you're mounting the display to a test dummy for?
Yeah. So absolutely, it gets complicated, but yeah. So we have, obviously we're in charge of the display, so we can intercept the display directly. And so we were working on what would be an appropriate jitter metric. We were working with the computer vision guys on that. For the audio and for, we of course use head and torso systems to capture the sound quality. And so that we have certain targets. For the vibration itself, again, that was just a laser and accelerometers. And there was just sort of specialty jig I set up downstairs that we just set that up to test.
So that covers it for now for the Steam Frame VR headset engineering discussion. We have a lot more from this trip, though. So we met with one of Valve's engineers who worked on the Steam Deck, and he has some really cool discussion about the deck versus the deck OLED, about PCB layout and engineering and design and things like that, challenges they ran into. It's not about a deck 2, but it is super interesting information, really fun discussion. That'll go up separately, and we'll look around and see if we have any other interesting clips to put online too. But for now, that pretty much covers the Steam Frame VR solution, and we'll have plenty more to talk about with the Steam Machine and probably with the Steam controller as we approach the actual launch in 2026. But in the meantime, make sure you check back for the Steam Deck conversation. Our policy is to pay for all of the travel and hotels ourselves for all these types of events, so if you'd like to support us in doing that to maintain our independence when we're doing reporting in the field, you can go to store.gamersnexus.net and grab our new Retro IO themed coaster packs, complete with 5.25-inch drives depicted on one of them and a floppy disk in the slot, an old school controller with the original colorways, an IBM Model M inspired keyboard numpad, and a retro-style GN logo. All of these are coasters in the coaster pack. You get one of each of these, or you can go to basically what's a self-funded Kickstarter-style campaign we have for our AI surveillance dystopia coverage coming up, where we have a whole deep dive series digging into things like the NVIDIA Palantir relationship, a raid of a normal person's home over a development console, and multiple other investigations like GPU export control violations and things of that nature. So head over to the store.gamersnexus.net, and check out our AI Dystopia Kickstarter-style fundraiser we're doing to help produce all of this great content and start putting together the travel, especially for our road trip around the US for several of the data center site visits. That's it for this one. Thanks for watching. Subscribe for more, like to catch the deck footage, and we will see you all next time.